Welcome, everyone, to The Explainer. So, did you know that a single, simple mathematical equation in genetics can literally dictate the future of millions of dairy cows all around the world? It's wild. Today, we're opening up one of the absolute coolest toolboxes in the biological world, the genetic toolkit. If you've ever wondered how animal breeders systematically control traits or upgrade populations or essentially design the future of an entire herd, well, you are in the exact right place. We're going to decode the complex, highly calculated mating schemes that take basic genetics and turn them into predictable, repeatable science. We'll be looking at everything from the really intense focus of inbreeding to the explosive growth of hybrid vigor. So grab your mental notepad and let's get into it. Okay, here's our roadmap for today. First, exploring mating schemes. Second, inbreeding and line breeding. Third, the power of crossbreeding. And fourth, outcrossing and breeding up. Let's jump right in. Section 1. Exploring mating schemes. The breeder's master plan. A mating scheme isn't just some random pairing out in a pasture somewhere. It's a highly calculated strategy. It's literally a mathematical, deliberate blueprint for pairing animals. The whole goal here is to control specific traits by manipulating the genetic relationships between the parents. It's the absolute foundation of our genetic toolkit, basically replacing guesswork with predictable, repeatable science. Section 2. Inbreeding and line breeding, looking inward to lock in traits. So inbreeding is basically the mating of animals that are more closely related by descent than the average of the general population. And it does a few really specific things. First, it increases homozygosity. You can kind of think of this as creating genetic twins at the cellular level, matching up pairs of genes to lock in very specific characteristics. Second, it brings recessive genes together. Now, to be clear, it doesn't increase the total number of recessive genes in the population. It just forces them to pair up so they actually become visible. By doing all this, a breeder can successfully fix specific characters in a population. And when you combine this with careful selection, it vastly increases phenotypic uniformity. You end up with a herd that looks and performs with this incredible, predictable consistency. Let's actually break down how this works mathematically, because there are three pretty intense forms of inbreeding. Step 1 is a sire-to-daughter mating. So if a female offspring has a mix of genetics, let's just call her AB, she's mated back to the pure A sire. Step 2 is a son-to-dam mating. For example, an AB boar mated back to a pure B female. And step 3 is the tightest of them all, brother-sister mating, where an AB offspring is mated with another AB offspring. This is genetic focus at its absolute maximum, rapidly accelerating that cellular twin effect we were just talking about. But what if you want that focus without going to those extreme lengths? Well, that brings us to line breeding. This is a much milder form of inbreeding that's heavily used in purebred populations. The goal here is to concentrate the inheritance of one really exceptional ancestor, like say a legendary champion bull, without narrowing the overall genetic base too quickly. A really classic example of this is half-sibling mating. You're still keeping the genetics in the family to preserve those elite traits, but you're giving the overall genome just a little bit more room to breathe. But here is the critical question. When you breed inward too much, you eventually hit a biological wall known as inbreeding depression. Traits get weaker, fertility drops, growth slows down. So how do we reverse this? How do we fix inbreeding depression once it actually sets in? Section 3. The power of crossbreeding, expanding the genetic spectrum. When a herd hits that inbreeding depression from way too many identical genes, you have to take the absolute opposite approach. We achieve something called hybrid vigor, or heterozosis, through increased heterozygosity. By introducing completely unrelated diverse genes, the offspring experience this massive boost in biological performance. This burst of vigor essentially masks those paired recessive genes that were dragging the inbred lines down, immediately restoring vitality to the whole population. It's like flipping a switch. The most fundamental strategy to make this happen is the two-way cross. This just involves mating two completely unrelated, different breeds. A classic example in swine production is mating a large white with a landrace. That creates a really robust, fast-growing pig that's just perfect for the market. The resulting crossbred offspring benefits heavily from the hybrid vigor of both parent lines, perfectly combining the best baseline traits of each one. And we can actually take this math even further to solve more complex production challenges using a three-way cross. Step 1, we mate breed A with breed B. The offspring is exactly 50% A and 50% B. Simple enough, right? But in step 2, we take that AB crossbred female and we mate her to a purebred male from a completely new third breed, breed C.
The resulting ABC offspring has this really fascinating genetic split. It's 25% A, 25% B, and 50% C. Now, why would we do this? Because you are continually injecting fresh genetics. You might be combining the excellent maternal instincts of breeds A and B with the incredible rapid growth rate of breed C. It's a total win-win.
Now, if you want the ultimate genetic diversification, we use the four-way cross, which is also known as hybridization. Step 1, A and B create a 50-50 cross. Step 2, somewhere else entirely, breeds C and D are mated to create a separate 50-50 cross. Then, in Step 3, we bring those two distinct crossbred lines together. The AB is mated with the CD. The final ABCD offspring is precisely 25% A, 25% B, 25% C, and 25% D. This is essentially a four-part harmony of genetic hybrid vigor. In the real world, this means maximizing disease resistance, meat yield, maternal ability, and climate adaptability, all packed into one single highly optimized generation. Pretty amazing. Section 4. Outcrossing and grading up, refining and elevating bloodlines. So, what if you want to keep your breed pure, but you desperately want to avoid that inbreeding depression? You use outcrossing, which is sometimes called pure breeding. This is the mating of strictly unrelated animals within the exact same breed. For instance, mating a landrace boar to a completely unrelated landrace sow from a totally different part of the country. You perfectly maintain that purebred landrace standard, but you increase the internal genetic diversity just enough to keep the offspring vigorous and super healthy. Finally, let's explore one of the absolute most powerful long-term strategies in the whole toolkit: upgrading, or grading up. This tool is specifically used to improve the bloodline of a native or maybe a lower performing breed by continuously introducing a superior purebred line. So we start with the parents. Breed A, our superior breed, crossed with breed B, the native breed. The offspring is 50% A. In the first filial generation, or F1, we mate that cross back to the pure A breed. Now we're at 75% A. We repeat this for the F2 generation, crossing back to breed A again, pushing the genetics to 87.5% pure A. And by the time we hit the F3 generation, we reach 93.75%. Just let that number sink in for a second. In just 3 generations of systematic, calculated back crossing to the superior purebred, you have almost completely replaced the native genetics, creating an animal that is virtually indistinguishable from a purebred. This means a farmer in a developing nation can literally take a locally adapted, low-producing native herd and in just a few generations upgrade them to high-yield purebred status. That is the incredible mathematical power of grading up. And that brings us to the end of our journey through the genetic toolkit. From the really intense precision of inbreeding and line breeding to the expansive power of crossbreeding for hybrid vigor, all the way to the refining elegance of outcrossing and grading up. You've seen the blueprints and you've seen the math behind the magic. So my final question to you is this: understanding how these completely different mathematical strategies can be deployed in the real world, which tool from this genetic toolkit will you use to shape the herds of tomorrow? Because in the world of genetics, you aren't just breeding animals, you are literally calculating the future of agriculture. Thanks so much for joining me on this explainer. Keep learning, keep analyzing, and I'll catch you on the next one.